Jack Chen, our group's rising star, if you want. But anyway, this is the TH seminar, whatever TH stands for. Professor Kai-Feng Chen, or we all call him Jack. He also calls himself Jack. Is a alumnus all over, starting with undergrad at NTU Physics, got his master's at NTU Physics, and also received his PhD in this department in 2005. And I would say by the time he receives his PhD, he is already equivalent to an experienced postdoc because of various reasons. And at that time, he opted to stay as a military service postdoc. So he had to stay further with us. Actually, he never left us. But he's a great success case, and one that I myself somewhat reached in terms of potential inbreeding, because it's such an outstanding case. So I don't want to repeat his achievements from first in the Bell experiment, and today's going to tell us about what he has done in CMS. But at the end of 2007, I myself was surprised when the KK spokesperson, the Bell experiment spokespersons approached me that they actually wished, but asking me to nominate Jack to the first installment of the IUPAC Young Scientist Prize in Particle Experiment, a biannual prize, the first time. So I obliged happily, but I must say I did not have confidence. I said, okay, very good, let's do it. So then sometime in late spring, he told me that he received it. So that summer we were all very happy. And then interesting thing happened that Tokyo University wanted to hire him. So thanks to Todai, and we worked with the university president, we managed to push through a special appointment starting at the end of 2009. So today is also a special seminar for Jack. He did not really ask for it in the real sense, but because it's a faculty requirement that it's also not himself directly seeking promotions, but he's qualified for it, he was notified for it, and why not? Okay, so that's a long introduction, but I think it's also a good opportunity for Jack to review before the new run a year from now, what he has done in the last 5 years or so, 6 years, when he seriously joined CMS since 2008. Okay, Jack, the floor is yours.
Yeah. Thank you. Thanks, George. Yeah, today I'm happy to introduce you what actually I was focusing on during past few years at CMS. So mostly we are looking for so-called heavy quarks. So this heavy quark means they're really heavy, heavier than top. So it's slightly different from what I did before, but it's very interesting, I would say. So today I'm going to summarize what we did and everything what we saw. So the first thing is that this is a standard model. I think people sitting here knows this a lot. And there are 3 generations of fermions. There's 3, and 5 bosons. Now we add the Higgs back.
The only thing I don't like on this picture is the neutrino should be the top and the lepton should be bottom.
Okay, good. That's
T
true.
equals to plus minus 1/2.
Okay, this is a good point. Yes. Next time I can reverse the order. Yes. Good.
It's a common projection, though. Because
Well,
neutrinos are a little bit
doing
on
this,
the
but,
outside, not on the inside.
That's right. Yep. Just want to say the standard model describes how those particles interact with each other and how everything works. But I think everybody can ask the natural questions that have we found all named? They have a really elementary, or this kind of question can be always addressed. So maybe the history can still repeat itself. For example, this is what we know about the periodic table 100 years ago, more than 100. We don't see so many, but today we have many, and they are still increasing. So in some sense, if we can find more particles, and maybe we can help us to understand the picture behind, because nowadays we know all those things because they are due to different numbers of protons, neutrons in the nucleus. So maybe by finding more particles, more elementary particles, may help us to understand what actually behind. So this brief history. So we have to come back. So why we need 3 generations? And this is a very classical one. We need 3 generations of quarks to produce at least one compressed phase in the mixing matrix. So that gives us a difference between matter and antimatter. But however, the KM model does not limit the number of generations to exactly 3. It can be more than that. So this is the beginning of everything I could say. So adding one more generation of quarks, or whatever new quarks into new fermions into the model can actually see a very obvious extension to what we know by now. And we know this is not really excluded by electroweak precision data. And so far, there's several constraints we already know, such as the mass between these 2 new generations cannot be too big because they are heavily constrained by the WBK. And also some low energy measurement, like from Fraser physics data, can constrain somewhat a little bit of the new quark, but it's not fully constrained as well. But however, many people know the death of 4th generation was dead before. So it's a classical death, I want to say, because PGG, our Bible, says an extra generation of ordinary fermions have been excluded at 6 sigma level, which is very difficult to say. But however, nowadays we know this is not totally true, because this statement was based on this parameter. But however, there's a very strong assumption followed by this statement, because they assume the 4th generation must be degenerate, and the matrix must be, a KM4 matrix must be unity. So it's probably beyond the so-called the truth anyway. So this is how this so-called 6 sigma is.
So if it's degenerated, then this contribution should be equal to 0.
Yeah. Somehow that's true. So this statement is not accurate anyway, but most people read the first one, but ignore the second sentence anyway. So the exclusion of the 6 sigma was covered by this kind of 2 strong assumption. But in reality, if you take out these 2, it basically no real constraint at all. So it's not really
So
that.
how do you call it a 4th generation?
Yeah.
Why it's a 4th generation if it's a no KM
No,
sort of
unit.
mix?
Right.
Unit.
Yeah.
In one sense, then it's a 4th generation.
That's right. But I think what he says is, well, can be any extra generation of fermion. So anyway, put things in.
What do you mean? This is the standard 4th
It's
generation.
a standard one, I think.
Yeah, but then it doesn't mix with the first or 3rd generation with a unitary mixing, or
Yeah, it's
maybe
mixing.
5th or maybe 6th, and then
Right.
in one sense it's a 4th generation.
You mean it's basically unity together.
The right-hand plot is the genuine sense of a 4th generation. Your question is about the
The
too
left-hand
strong
one.
an assumption. Your point is saying, assuming a 4th generation that doesn't even mix, but this is the original mindset of PDG. So the right-hand plot says that if you squeeze the degeneracy, and then allow CKM freedom, then there's actually much more parameter space in electroweak physics.
Yeah.
So, but I don't understand why this unity is not a requirement.
Well, what do you mean?
The unity of
Unity,
system.
not unitarity.
Yeah.
Unity.
It's unity, it's 1-1-1-1. It's not unitarity, it's still required, but unity is different. Yeah.
Okay.
Yeah. So it means no mixing. No mixing and no interaction, so it's basically not a real 4th generation in sense, just what Xiaopeng said. Yeah. Well, but actually, there's another very strong constraint. It's mostly from this measurement. It's the measurement of invisible Z decays to something we don't know. But if we take all the invisible Z decays to be from light neutrinos, then we can actually measure how many neutrino flavors we have. So from this measurement, we know from that actually is exactly 3. They're very precise. So this is a very precise one, but however, this does not exclude the chance that the neutrino is heavy. Actually, it's like a heavy neutrino. If the mass of neutrino is above like 45 GeV, then this is not really a strong constraint in that sense. But why we say this so precise, because if you look at the plots, the error bar was increased by hand by factor 10, which is pretty interesting because they want you to see the error bar. Otherwise, you don't see, just see a dot. So it's very precise measurement.
But Planck tells us that Nu is about 3.4, right?
Yeah, this is how I'm going to say. Exactly. So from the astrophysics data, that the so-called effective neutrino number for CMB is actually 4 point something. Well, actually, it highly depends on model. So this is what they say called a white paper. Also, I do not really understand how they did this, but the all different model, different way of constraining will give you a different number of effective number of neutrinos. And actually, you see, most of them are actually above 3, and many of them are above 4 actually. So at least 95% confidence level. I don't know how they calculate, but they should greater than 3. So this is kind of interesting. So this actually give us some kind of hint that somebody may need a heavy neutrino, which is actually beyond this, what we know by now. And this is interesting. But however, the newest data for Planck actually somehow pushed back to 3.3, and everybody now is concerned with 3. So it's a little bit hard to say by now. But the old data actually is more look like a 4 generation, but now it's 3. But anyway, so this is still hard to say for now, but we still can move forward, I will say. And there's another old indirect hint from so-called 5BS. This is so-called what people call first evidence of a new phase. The title is very strong, using the B2S transition. It's pretty old, in 2008. Well, what they did was actually measuring this 5S is a mixing phase from B sub S meson. And they do see some kind of deviation between this is a prediction. That's what they measure. But however, if one add the fourth generation quarks, it can be easily push this to push the prediction to match the data, which is pretty good. But
so are these going away?
yeah, it has been gone, right? Because our dear LGCP kills all this kind of new physics hint. This is a winter 2003 version, and the 2013 version, and the standard model prediction here, and the data is just like the 1 sigma. So now it's more or less consistent with the prediction, unfortunately, anyway. But I think the people here know George is one of the most selling point about the fourth generation is about this BAU issue, is a barogenesis issue. The idea is just like this: from the like W-band measurement, we know the matter and the antimatter. The asymmetry between matter and antimatter should be like a 10 to minus 10 level. But if we take the Kobayashi-Masaskawa model, that can only give us like a 10 to minus 20. So we need some way to solve the 10 to 10s issue. And adding this fourth generation quark is something easy to reach this kind of strong enhancement. So if we go back to see this ingredient for CP formulation standard model, we need at least 3 generations, and one need a non-trivial CP phase, and the unitary triangle must be there, cannot be a 9 or something else. And one thing usually we have to highlight is the quark mass cannot be degenerate. So if one can simply shift, assuming the contribution from a one heavier generation from the lower 3 to higher 3, one can easily boost this total CP symmetry from 10 to minus 10 to 10 to minus 20 to by 10 to 13th order, 10 to 15th order. So it's pretty nice. So it's a very low cost solution to this barogenesis. You just add 2 more quarks. So relatively easy.
Yeah,
So-
but this is just only 1/3 of the story, maybe even not 1/3.
Right. Not even one. Sorry, that's true. But anyway, just want to put the why we work on this and the old stories. And this is already mentioned by the old paper from Yaskov already. So and everybody knows the Nobel Prize already gave to these 2 gentlemen last year, and the quote-unquote Higgs boson have been found. So you see, this is not formed in a day, and the take time and the Higgs increase, and we do see some extra bond between this is what we know is Z, and this is probably contributed by 2 Z bosons, and this one is the Higgs boson, quote-unquote. So the issue is like this. if we're adding the Higgs and then adding this so-called fourth generation quark, the new quarks are supposed to be heavy. That's what we understand, at least heavier than the top. So that means this new quark will have a very large impact on the Higgs sector. For example, the Higgs production is that's the dominant one, gluon fusion through top loop and produce the Higgs. So if we have one more generation of a quark, like for example, you replace the top by a heavier top or a heavier button, then it can easily increase the production rate of Higgs by a factor 4 to 9. Yeah.
It's not quite true,
Yeah, is that question?
because now MH is below 2 MT,
Yes.
so the top or T prime, they will behave in the same way.
Yep.
It's in the non-decoupling limit,
Yes.
so they both will contribute about in the same fashion. So it's not quite a factor of 4 to 9.
Mm-hmm.
It will enhance, but not in the same way as MT prime square over MT square.
Yeah, but it's not. I think the calculation here is already assumed the top T prime, B prime to be like 1 TeV level, so to be far above the mass with Higgs. So it's
But
like
still-
counting number of fermions.
That's right, that's right.
Yeah, so it's not really contribute like heaviness, but it's just like a additional fermion you contribute to the loop anyway.
Okay, so
Yeah.
you are thinking about
It's a
3
T.
square.
Yeah. So it's a square times 3. I mean, instead of 1 top, but now you have 3 fermions. Yeah.
I was just trying to help.
Oh, okay.
Don't say MT prime over MT,
Oh, okay. Yeah.
Okay.
No problem.
because it's in the non-decoupling limit.
Yes.
The mass doesn't matter.
That's true. Yes. So yeah. So this is how this factor 4, factor 9 actually comes. But the so if we have this big factor on the which can enlarge the Higgs production, then then we can already see a Higgs boson much earlier, or we don't see it. So this is a so-called limit plot we usually put. This is assuming the Higgs production is according to the with two more quarks in the loop, and this is what we have. So that means we already excluded all the phase space that have been done up to now. So, but sure, this does not match to what we saw in the data. This is the golden peak. It has for the Higgs equal to 126 GeV, and we line up. And with all the axes correctly line up, you see we don't see the hint. So the issue is like this: we see a particle, and all the properties of like this quote unquote Higgs decay, like or the spin parity, they are all consistent with the current hypothesis of a standard model Higgs. So if one assumes this Higgs boson is a pure standard model Higgs, and then the assumption of a pure standard model plus fourth generation will be difficult because they are conflicting with each other. But however, this also gives us some different way of thinking. We know this so-called sequential fourth generation quarks are become constrained because of Higgs. But however, new other models like something like factor-like quarks or any exotic quarks, non-standard model like fourth generation quark, can be still survive in the picture. And sometimes we can even say this can be an alternative solution to the fine-tuning problem in the Higgs sector. Like instead of SUSY, here it is stop, but you can replace the stop with something else like a factor T or something. So it can be done. So and it can be also have a different way of motivation. So in any case, we think the direct search for new quarks is still a must-done at LHC because LHC is the best place to look for like heavy objects like this, and they have strong interactions.
Why do you put that as dashed lines in the second diagram?
Well, actually, I don't think this correct way of drawing, but anyway, this is from Wikipedia.
Wikipedia. But then it's not a vector-like quark.
Yeah, it's nothing like what. This is stop. Yeah,
stop.
the stop loop. All right, so I'm going to talk about what we did at the Large Hadron Collider, and we are doing a CMS experiment. And this is a CMS detector. I'm not going to the details, but the journal says this is a very general detector, and can look for many things. And this is not the biggest one, but probably the heaviest detector so far used by human beings. This is a man, so this is still pretty big, like 5 levels tall. And this is a real picture of the detector. On the inner side, we have a silicon tracker, and which can record the charge track activities, and what we call eCal can measure the energy of the electron and the photon, and HCal, which can measure the energy of the hadron tracks, hadron particles, and this magnet, and also the muon system. So in order to maintain such a big detector, we need a lot of people. So at CMS, we have more than 3,000 people working on different things. This picture probably only consists of 1/3 of the total people, but it's
Less than
already maybe 1/4.
Less than 1/4.
Less than 1/4. It's hard to count anyway. I don't want to count the number of people here. And well, I'm not sure. I'm not inside, right? I cannot remember if I took this photo or not. Anyway.
Me neither.
Yeah. Yeah, I just want to put one slide to tell, because we do have students here, although we do not have many, just want to let you know how we actually take a look into particles. We cannot really control everything, but in general, based on detector design, we can look for those particles. Like the muon usually have a track inside the detector, and we don't have energy loss in the colorimeter, and the muon can penetrate to the muon chamber, so that we see like S-shape curve on the detector. And for electrons, we have a track and eCal shower. For charged hadrons like a proton, pion, kaon, they just have a track plus an HCal shower. And like the neutral hadron, like the neutrons, they will have no tracking, but they have an HCal shower. Photon is easy, also no tracking, but with eCal shower. And what we usually use is what we call jet. Jet in our jargon is almost like means a light quark or a gluon going through the detector, and then they hadronize into many particles. So they will generate a lot of tracks, a lot of eCal and HCal shower. For neutrinos, it's difficult. Well, what we have is I try to measure the imbalance of the energy in the detector and assume the missing part is due to the neutrino. So this is how we detect all the particles. Yeah.
Quick comment, since you are giving this
Yes.
table. A heavy charged particle will affect Higgs decaying into gamma gamma. The discovery of Higgs was announced in the Higgs to gamma gamma.
Yeah,
So
gamma
now-
gamma and 4 lepton.
Right,
Yes.
so if you have, let's focus on gamma gamma,
Mhm.
because then any heavy state
Mhm.
that is charged will contribute.
I mean Higgs decay. Yes,
Yes.
that's true.
So therefore, you have double enhancement that will immediately tell you something cannot fit.
That's right. Yes, that's true. Yeah, it's not only the production but also the decay.
Correct.
Higgs decay through the loop.
Correct.
Not like this. There, I think the W dominates.
I think it's still
If
W
you-
dominant.
So the fermion loop and
How about a
boson
factor of 3, then squared?
loop. I think for Higgs to gamma gamma, the W loop dominates.
Okay, the W contribution to the top is about 7 to 1.
Yeah.
Now, if you have 2 extra more,
Mhm.
then I'm not sure W is still the dominant contribution.
No,
in
no
fact,
papers on
in fact, the fourth generation for
Suppress it.
gamma gamma can be very small because the higher order correction
Mhm.
and make it much smaller.
Oh, really?
Yeah.
Uh-huh.
So it's the production glue to Higgs make it an enhancement and line
That
factor.
cannot be
But then
circumvented.
Higgs because to gamma gamma with the fourth generation can make it much smaller. So even it's smaller than the third generation. But then that's what the present sort of.
Now, if there is a
Trying to help.
destructive interference,
Yeah, I tried to
Mhm.
help that give.
if there's a destructive interference between the W loop and the fermion loop,
Yes.
then of course it will be much smaller.
Okay.
It will first be much smaller, I think, if you have a 4th-generation like object. Basically, it will be a suppression.
Mhm.
Because you're 7 to 1, it's very close.
Okay.
Then they use the W as George.
W.
W and
Vector
Z,
mode. Yeah.
that's an enhancement, that's a enhancement.
That's why that's Okay. Anyway. Okay, so let me move to the real thing we did. So by assuming we have 2 more quarks here, we assume that the standard sequential Bose-Einstein quarks. So in principle, they will decay through this kind of a to like either T prime can decay to B prime or B prime decay to T prime, depends on their mass. But in principle, the lighter one will always go to the 3 generation or even lighter generation. So we can do this kind of assumption. They always combining with a W or something to become the rather complicated decay. So if one can have like a T prime particle, like a radical of the top, but this is heavier and decay to button and W, it will produce a B and W, or even go to lighter one like a Q and W. So it's not really different from a top, which is like a B and W, but the mass is somewhat heavier. But if this is a B prime, then suppose if you go to T prime, in this case, we'll generate 2 more W's. So that's in one event, if we have a 2 B prime quark, will become like a 2 B quark plus 4 W. So it becomes rather complicated. So it's very complex. Well, if we go to like lighter quark plus W, it's just like a heavy top in any case. So well, the decay between these two is hard to say because they usually depends on their mass and how it works. So some analysts can assume one is heavy, another is lighter, or reverse way, and see how do we do. So I'm going to cover a big list of what we did during the past few years. Some of them are heavily contributed by NTU people, or some of them are contributed by our colleagues. This is the first one, pretty old one, but it's pretty interesting because they just look for 2 isolated leptons plus 2 B jets. Assuming this is a D prime decay, but in two lepton in the final state. So this is the total decay picture like this: T prime and T prime bar decay BW, and W decay to lepton neutrino. So this is like 2 B jets plus 2 leptons, and they must be at the opposite sign. So the idea just like in this analysis, we try to squeeze all the background into a lower corner of the this is the lepton B jet infrared mass. So push your background into one side and make a hard cut. So in this case, background which is like a standard top is seldomly jump to the higher mass side. So in this case, we can have a very good sensitivity to the heavier top rather than the standard top. So based on this, one can set a really heavy limit because from the previous part, you will see that we only see one event in the data. And then one can calculate how many background we are expecting. Actually, we're expecting 2 and seeing 1. So this will give us a fairly strong limit, about like 557 GeV by using the 470 EV data we have. And the surely this dilepton channel. So one can also look for a different one, like W go to 2 hadrons, like 2 quarks in this case. So in this case, since there's only one neutrino, so we have no ambiguity. So in this sense, we can actually control the full picture by assuming like this lepton plus the missing energy become a W, and another 2 quark become a W, and the top, these two should become a so-called T prime mass in our sense, and these 2 mass should be the same. So that means we can actually fully deconstruct a particle with at the right mass. So that's how we see. So this is the so-called what we call the fitted mass. This is equal to the mass of these 2. So if the standard top, we have the peak here, which is the right place, but we have long tail to the right hand side. But if this T prime, for example, like 550 GeV T prime, we have a peak at the right place. So such an information can give us a very nice information about the mass and do we see any extra peak through this long tail over the top. But sure, this signal is not very big. As you see, this signal here, T prime signal is already boosted by a factor of 20. So, and the analysis can be done in 2 channels. One is electron, another is muon. So basically, they look similar. And we also realize that not just the mass, one can also sum up all the energy in the transverse energy of all about objects like jets, muons, leptons, and the missing energy in the event. And they also have a good sensitivity to such a thing. Like as you see, also this broader because there's not really fitted the mass, but they still have some sensitivity to separate signal in the backbone. So means we can combine the information together in such a way that the things can go in 2 dimensions.